Why are these the permutation and combination formulas? What's actually happening here? Let's find out. Welcome to Howie's Hypothetical Ice Cream Shop, where we have 10 different flavors. And for today's special, we have a permutation cone or a combination bowl, where you choose 3 different flavors. Now, what's the difference? Well, with the permutation cone, order matters. If you say vanilla, chocolate, strawberry, that's going to be a different experience than strawberry, chocolate, vanilla. Versus a combination bowl, order doesn't matter. No matter how I scoop it, it's going to be the same experience for you because you can eat it however you want. So however I place the scoops really doesn't matter. Now the question is, how many different orders are there? Let's start with the permutation cone. Remember, we have to pick 3 different flavors. So for the first scoop, there are 10 options to choose from. Then you can't repeat a flavor, so there are 9 options for the second scoop and 8 options for the third scoop. And then we multiply these to get the answer. But why do we multiply? We can see this with a diagram. We have 10 options to choose from, then 9 options, then 8 options. So we have 10 branches, where each of those branches have 9 branches, and each of those 9 branches have 8 branches. So we would have 10 groups of 9 groups of 8, or 10 times 9 times 8, which is 720 different orders. Now 10 times 9 times 8, that's the beginning of 10 factorial, which is 10 times 9 times 8 all the way down to 1. So how do I write this so I only have 10 times 9 times 8 and not the rest of this? Well, we could divide 10 factorial by 7 factorial, because all of these would simplify to 1, leaving 10 times 9 times 8. So with the permutation formula, if we have 10 flavors and we have to pick 3 different flavors, we would have 10 factorial, but we can't write 7 over here because our original numbers are 10 and 3. So how does 7 relate to 10 and 3? Well, 7 is 10 minus 3. So instead of 7 factorial, let's write 10 minus 3 factorial. So generalizing this, let's replace 10 with n and 3 with r. So we get n factorial divided by n minus r factorial. We could think of this as just wanting part of n factorial. Now with the combination bowl, order doesn't matter. It's not like the scoops are on top of each other so they have to eat it in a certain way. They can eat it however they want. So whether they say vanilla, chocolate, strawberry, or chocolate, strawberry, vanilla, they're going to get the same experience. And this is true if they ordered 4, 5, or 6 different flavors. We're not caring about which flavor is next to which flavor, we're just caring about which flavors did they choose. Now I want us to think about permutations for a couple seconds. Remember, there were 10 times 9 times 8, or 720, different orders for permutation cones. I want us to imagine that list of 720 different ways. Every group of 6 now count as 1, because order doesn't matter. All of these were different in a permutation cone, but they all count as the same order in a combination bowl. Now, how do we get 6? Well, if you already know your 3 flavors, there are 3 options for what you're going to say first, 2 options for what you're going to say second, and 1 option for what you're going to say last. So that's 3 times 2 times 1, or 3 factorial. Now, to see how many different combination bowls there are, we would divide the number of permutations, 720, by 3 factorial, because every group of 6, or 3 factorial, now counts as 1. 720 divided by 6 is 120. And to generalize this, let's have our 10 be n and 3 be r, so we can see that we would have the permutation formula, but divided by r factorial, because every group of r factorial counts as 1. I like to write it like this, but a lot of the time the formula is written like this. So with the permutation formula, we just want part of a factorial, and the combination formula is just the permutation formula, but we divide by r factorial because order doesn't matter, and every group of r factorial now counts as 1.